Hey, hello there, and welcome back to another video. So, Advent of Code, day 22 it is. In previous videos we have solved part 1, which was kind of a sludge, and it was much more complicated than I thought it would, although compared to part 2, it's relatively easy. So, part 2 now, you have to think in 3D. So let's go maybe a bit back of what part 2. Part 1 is about. We have this weird map, and where we can walk along the dots following these instructions that are below here. And the idea is that if you go out of bounds to the nothingness, if you're here, for instance, and you turn right, you wrap around and appear on the other side. And when you hit one of these hashtags or hash symbols, they block your walking, and you're stuck there until you turn around and do something else. So that is part 1, and well, it is done. But the idea in part 2 is that this same map is actually the unfolding of a 3D cube. So you can see that this map here, it's made of squares of 4x4, and those squares correspond to the 6 faces of a cube. And the actual input, well, it's the same, but the squares are much bigger, are 50 by 50. This is 50 pixels, or 50 characters here, and 50 characters tall. And the unfolding of the cube is different. It's a different shape, basically. And the idea, well, is that if you go, well, maybe it's better to explain it with an actual cube. So I have a Rubik's Cube here to help me think about this thing. So the idea is, for example, if you are walking here on the orange side, and you go up, and then you need to go up again, you would go to the white side, instead of like teleporting around like it was in the part 1. So it makes more sense, actually, the movement. But it's difficult to project that into 2D. So for example, if you are here in this place, and you move left, you would go to the face that touches this on 3D, which will be this face here, this 4x4 thing. And I guess you will appear in here. Sorry, in this position. So it's not very easy to see, but yeah, you basically have to connect these things. And well, all of this is more complicated because the unfolding in the example is different than the unfolding on the real input. So I've been thinking a little bit about this, and it's complicated. Like, if you try to, I think if you try to actually understand this unfolding and represent the cube as a 3D thing in the code, and then like working in 3-dimensional space, that could work, of course, but then you have to still give the answer, like the final answer depends on your row and column on this 2D map. Like, you still have to, if you do that, all of that projection into 3D, you still have to, in the end, like, unfold the map again, unfold the cube again, and see where you're standing, how it corresponds to the 2D coordinates. So I think that actually doing all of that transformation, on one way to the 3D, like from 2D to 3D, and then the other way around, I don't know, seems like unnecessary work. And maybe we could do something simpler, like walking in 2D, because like as long as you don't go out of bounds, you can still walk around in 2D here. Like here you go from this face to this one, but you can still thinking, like if you're here and you go down, you're changing faces of the cube. But in 2D, it doesn't matter, it's still like you're going down. So that's also another observation, I guess. And yeah, that's as far as I have thought about this. I was also thinking about another maybe possible idea, which is to, like, if you actually want to model this thing in 3D, you probably have two ways of doing this, or well, maybe a lot of ways of doing this, but the two ways that come to my mind, you know, as more obvious ways, would be one of them would be to represent the cube as 6 faces, and then your coordinates in the face itself. So your current position will be the number of your face, like 0 to 5, and then your coordinate inside of that face. And if you do that, when walking to another face, you would have to know like which faces are connected to what, to which, in which direction, and then how to sort of rotate your direction depending on from which side you come. So for example here, if I'm walking on this orange face and I go up, let's say that this is the up direction in this face, then I will go to the blue face on this side. But if I am walking on the white face and I go up, I will also go to the blue face, but appear on another side. So maybe depending on how the blue face is represented in memory, the side that you appear depends on which other face you're coming. So it's not you know, it's not too simple to think about that. You would have like, but I guess you could hard code all the different possibilities, so all the different movements. Each face is connected to 4 other faces, so that would be 6 times 4, like 24 combinations of movements. Or I guess also you have to think of the reverse too, so maybe it's 48 combination, like when you go from one hand. Oh no, I guess it's 24, right? Because that would include also the inverses, so it's 24. But yeah, the problem of course of doing that in 3D is that then you have to go to 2D like this. And another idea of going 3D is to think of like actually thinking in 3D completely. Like consider the cube to be or your position to be a 3D coordinate. So your positions here, for example, if you consider that the green face is up and the blue face is down, and Z, the third coordinate, is the height, then this would be at 0, Z equals 0, and this would be Z equal 1, and 2, and 3, and then being on this side, I guess on the blue side, it would be Z equals 4. And if you consider that, like if you go full 3D, you can consider sort of like walking from the perspective of one face. Advancing is always like the only thing that you can do in this challenge is either advancing or rotating to one side. But you can consider that your direction is always forwards. So for example, let's imagine that we are going forward here on the green side and we are in the middle. If we continue going forward this way, we are going to face the red face. But turning left, for instance, is the same as like turning everything to the right of the world, which I know that this can be done by using like matrix multiplications in 3D. But it's been like I learned a little bit about that long time ago, and I have forgotten about that long time ago. So that seems like a complex thing to do, but like it would simplify things in the sense that crossing from one face to the other would only mean rotating the world in only one only one way. It would be only one case instead of 24, but it would be a very like generic case. But still, going 3D that way still implies having to think about the going back to the while unfolding the cube. So I was thinking, well, what if we keep things in 2D and try to think of like more specific case, actually like my input's specific case, and try to code a solution like trying to solve only for this cube unfolding. So if I code it for my input, then it won't work. It won't be a generic algorithm. It won't work for the sample inputs. But at least if I can do it right, I will get the answer. So, and then maybe I can try to find a better solution or not. So yeah, that's what I would like to try now. And actually, I don't have that much time. At 6 p.m. or 6:30, I would like to leave to do some to hit the climbing gym. So let's think about this for a little bit. So one way that I was thinking about this is maybe we can assign each of these faces to one of the hypothetical, like maybe we can say that this first face is up, and then this one would be, well, one of the faces that connect to the up face. So for example, the right face. And if this is up and this is right, then this one, like we can think of the Rubik's Cube here. That's let's see if I can see the same as in the camera. So if green is up and let's say, well, orange is the front, like you are looking from the front here, then yellow would be the right. So okay, we know that if green is here and this is if this is up and this is right, then this other face should be the front face of the cube. By the way, I don't know if I mentioned that when in Rubik's Cube, and I guess this is something general to cubes. You can think of the faces of the cube depending on the orientation towards you. Like you have a top, down, front, back, left and right faces, and that's kind of like an absolute positioning of them. So we can think about that, and then I can think maybe about the Rubik's Cube and how things connect, and see, special case each of these out of bounds condition where we have to like teleport into the, because when you're thinking in 2D, we are actually teleporting. It's only when you're thinking in 3D that it makes sense as walking one of these edges. So, how do we do that in code? I have no idea. The first thing that I would probably want to do is extract all of this logic into a function and just simply call this thing part1. Yeah, just part1. We'll have a map which, let's fix the typings here. This should be a reference to map, and this can be a slice. We don't want to consume these guys. We can pass both of these by reference, and we can have this be the answer 1. And finally, we need to return this thing. And yeah, they should return a what? What are you expecting? I32. Perfect. So there we have part 1, and part 2 I'm simply going to shamelessly copy paste for now, because between part 1 and part 2 actually most of this code should remain the same. Like the way you calculate the final position is the same, the way you start is the same. Actually, all of this would be the same. Only this try advance function would be different, I think. And even in this try advance function, most of it or a part of it would be the same, and only the wrapping code would be different. But well, we can try to do a very ad hoc solution for part 2, and then once we understand things a bit more, we can maybe try to find a more generic. Oh, sorry. Once we understand this a bit more and what things differ from part 1 and part 2, we can see if we can reduce some of the duplication and make, extract things as necessary. So there's a problem here. Oh, there's an extra borrow here. Oh, because we were consuming these instructions, I guess we have to iterate through them. And now this thing is reference. That is all right. We can dereference here, I guess, or well, we can dereference here, right? Or I guess it makes more sense to do it here. Yeah. Okay, let's copy the same here. We have part 2. Yeah. Why don't you like this? Move out of a shared reference. Oh, these instructions are not copyable. Whatever. Sure. Let's make the borrow checker happy. And that's it. I think actually this try advance is also going to be different for part 2. Let's copy it for now. Try advance part 2. Yeah, beautiful code duplication, and let's use it in the part 2. I guess we can give some better try advance well, like I want to say, like this is wrapping around, and the other thing is in 3D cube or something. But let's think about names later. For now, part 1 and part 2 is clear enough. Okay. So, how can we do a very ad hoc solution for this? Let's do something. Let's do. Let's start by, when we go out of bounds on part 2, like let's try to see where's the first, what is the first place where we go out of bounds, and panic there and say went out of bounds on, I guess we can have x, y, going, and let's print out also the direction. Direction equals, let's say, dx and dy. And let's see. Let's see what happens when we cargo run day 22. Oh, there were. Well, I guess these things don't need to be mutable, but panicked. Went out of bounds on 58.0. Going to this is down, right? No, this is up. Yeah, and we are in the first column. So checking our, we can see maybe the input here. Wait, this is 58. Okay, so we are basically in this first phase. 58 is probably here. We bumped here, and we are trying to go up. Is this the first instruction? Let's. So we are walking 33, then left, which would be turning up. Yes, and yeah. So it's basically after the first turn, we are going out of bounds here, and we should appear somewhere. If this is the up, if we consider this phase to be up, and this right, and this front, then this would be going into the back phase. And we have to, knowing this unfolding, what is the back face? So maybe we can think, let me try to, so this would be front, going down from front, this would be the down face. Maybe let's make the size a bit bigger, smaller, sorry. So this face would be the down face of the cube, which makes sense if you are up and then you move down 2 times and you are down. And if you are down like that, turning left into the like this, I think this would be the left face, and then going down from here, it would be the back, right? Although I sort of forgot what I was using as a reference. So let's use, for me, the green as the top, and I don't know, white as the right. So this would be front red, then this would be bottom blue, then turning left here would be yellow, left, and down from here, so you're over here, down from here, it would be orange, which was, yeah, the back. So we know that we have to appear here on the back, but it's very difficult for me to understand. So we are going from the top face, green, to the back, but how we appear here on the back, because if I'm not mistaken, like these faces can be sort of rotated. Like it's not clear to me that going up from here will appear down here. In fact, I think will not be the case. Let's actually think about that. I'm going up this way, and this unfolding would be, top it would be with the bottom here, then front will be like this, then down would be like this, then left would be like this, then the back would be like this with the left side up. So we would be appearing on the left side of the back face. If I'm not mistaken, we should be appearing here, and on the top here. Like if we are here, we would be appearing like over here, like not on the bottom of the left face, but on the up part of the left face. That's what I sort of followed up looking at the Rubik's Cube, but it's very difficult to follow that. And maybe I could prepare, like actually do a paper cube unfolding of this thing and annotate that, and then transpose that to code some way. So I will pause the video and make a piece of paper cutting of the cube unfolding. I'll be back. And I'm back. So I made a cutting of the unfolding of this cube, of the cube unfolded, and I can, as you can expect, fold this thing into an actual cube. Very pretty. This is art. And I've also marked in this piece of paper, which I doubt that, you can see something, like what is the up face, and my cat also wants to play. What is the up face, what is the right, front, down, and so on, and the up directions of these things. So when you fold this thing, that's it, the cat now is on my lap. When you fold it and you have now the up face, and we know that we start in this up face, well, we decided that this is up, anything could be up, but let's arbitrarily define that this is up, and we are going up from here. We know that it's going to go to the back side, and yes, that is what we see here, but you can see that the back side is rotated. And actually, like if you follow along, if we are going up from here, we appear like on the left of the back side, if the camera captures something. And you probably don't see any of that because this is a very small portion of the screen. But anyway, like with this, I think I can have a more like visual representation of things and more quickly realize what is left or up or down from what, and how things appear when we go out of bounds. So that's good. Let's then try to express that in code. So what we could say is something like, okay, let's identify which phase you're in. We could say, well, if you are on position X from 51 to 100, and Y position from 1 to 50, then we know that we are on the up phase. And then if you go up from there, do that, like wrapping to appear on the back face, on the left of the back face. And yeah, we could distinguish which phase we are in depending on our coordinates. I think we could also maybe do something like having a drawing of this thing, and then mapping things to that sort of drawing. Something like this. Let me drink mate for inspiration. Okay. So let's say we are going to put this on a string. Our map would be something const map, whatever. This is gonna be a string slice. Our map would be something like, let's draw that same thing from the input, but in small. I think the unfolding is something like this. Right? Yeah. Yeah, it's 2 here, then 1 here, 2 here, 1 here, 2 here, and then down here. Oops. And if I can see my piece of paper, this could actually be like, we can mark this as the up, right, front, down, left, and back faces. So we have like a little drawing to access, like to know which face we are in. So if we get these coordinates, like the real coordinates that we have, and we divide them by 50, because we know like that is a hard-coded part of the exercise. These faces are 50 by 50. Then we would get the coordinates on this little map, and we can know the letter that corresponds to that face. And then we can think of, okay, what happens when we go, when we are on the up face and we go up, then we appear on the back face on the left or something like that, and do case by case, I think. So maybe this, instead of being a string, let's do it like as an array of stringies. Whoopsies. If I can type the right symbol, yeah, and this would be starts of strings. Yeah, this is the worst refactor ever. This close string, 2 spaces, close string, sure, like, can you provide a, yeah. Oh, come on, don't format it. Do not format it, I want it like this. How can we trick the Rust formatter to not format this? Maybe adding a comment here. Something. It still wants to format. Let's ask the internet. Rust form fmt skip line. now it is just like this. I don't know if this can be applied to, well, I guess I want to apply this to all of this. Yeah, that's fine. Now I'm saving and it doesn't reformat this. So yeah, this is like an ad hoc mapping. Let's call this thing face or cube map. That's of the cube faces for the particular cube and unfolding on for the cube unfolding on my particular input. Okay, and here we're going out of bounds. Let's say let's face B. Well, we're gonna access this cube map with some sorry. First with y coordinates divided by 50. Beautiful. And actually this is probably complained because this is as u size divided by 50, and then access these the same with the x coordinate as u size divided by 50. Okay, you don't like this? Oh, because these are strings. Yeah, as bytes, whatever. Give me them bytes. So we have the character that represents the face of the cube. Oh, this is a U8. It's not even a character. Can we? Well, let's do car, and that's it. So on dx, on xy, this would be face. And let's see if we did the mapping correctly. Yeah, face up. Look at that. Very nice. So now we sort of know which phase we are in. We can do maybe a big switch statement to correspond the phase and the direction we are going to what is the new position that we are going to be. I don't know if these things will need to be mutable. They probably will. Well, yeah, let's leave it, those things. We're gonna then switch. No, we are in Rust. This is called match. Sorry. Match a tuple with a face and the direction, which I guess we are gonna. Well, we can put in another tuple here. Actually, I will probably want to do that. Dx, dy, and if we are on the face up and the direction is up, I can write this as 0 minus 1, but I would probably like to extract that. Okay, we are going to think about that case, and then for any other case we are gonna panic. I don't know how to go from face in direction this thing. Okay, and yeah, this will be the case that we are working right now, right? Yeah, 0, -1. And I wonder, can we put this into a constant? Because we are going to be reusing those directions. I would prefer to read them better. So up would be these, which would be which would be a tuple of I32 if I'm not wrong. Can I use a constant here? Well, it seems like we can. That's very good. And then this is the same constant as we are using here, so we are going to have something very similar to this. I wonder if we can just copy this. Well, maybe let's try again. Ah, man. Okay, we are here. Let's go here, copy. Let's go here. Well, I'm a bit derpy today, so we're gonna have all of this, but we are actually right, down, left, and up. And these things, I think, are going to be the things that I will replace in here. Yeah, look at that. Does this thing... Let's also panic here and say, wow, too good. We should still be getting, sorry, I wanted to try and see if the answer to the first part, oh, I'm actually not using the answer 2, so let's run it like this. Yeah, I didn't break part 1 because I was not editing part. Oh, I actually, yeah, no, I was editing part 2. That's the problem of copy pasting and refactoring at the same time. So I did this for part 2. I also want to do it for part 1 because it is nicer to read. And just to see if I didn't mess up the directions, yes, it's still the same answer. Let's re-enable part 2 and print answer 2. So we have one less warning. And now we should be following this to-do case. Yeah. So we are here. How do we wrap this thing around? Well, let me remember, this should appear on the left. Yeah, on the left. And we are near the, we are on the top left or near the left of the up face. And we will appear then on the left side near the top of the back face. So we are going to appear in this face near the top here. So how do we do that? Like in terms of what is the new face, it's going to be, well, this back. But this will be then like 150 plus whatever x we were. I think we are going to need like to transform this x and y, do a mod 50 to have like the relative position on the face itself. So say phase X is gonna be X mod 50, and phase Y, and I know if you're thinking of don't repeat yourself, all of this hard coding of 50 is, yeah, it is noisy. I will make a const out of that at some point. But yeah, this is the position in the face itself. And then I guess another thing that we could do, like, what is the result here? Well, first we know of the direction, right? We will need to change the direction to, we were going up, and now the new direction. Oh, so this thing actually changes direction also. Like before, okay, so it's not the same code in part 1 and in part 2. We also want to change, like here we were returning the position. Now we should also be only the new position. Now we should also return in the new direction. Yes. Tile, if it's empty. Yes, and then we are checking with the wall. Yes. Sort of want to extract like tuples of these two things to make them be called points, but let's resist that urge for a little bit. So yeah, we want to check the tile. You know what? One of the things we're gonna calculate the new x and new y inside of this match, and we are going to then recalculate which tile we are in, and then we are going to do this check for walls on that tile. And finally, we want to have a new direction x and new direction y returning from here. New dx and new dy. And here we were going up. We now know that new I almost screwed something very stupid here. Let's start like this. Sure, new dx and new dy are gonna be, we appear from the left side, we are going to the right. So we are changing directions, and we also need to update the positions. So let's put some columns here. And this will probably need to, update the calling. So let's copy this and do the same thing as, no, this is try advance. We need to change try advance part 2, no, sorry, here in part 2, we will get these. Yes, and then we are going to, well, do something very similar to this. We are going to assign new dx and new dy to dx and dy, because this changes direction now. Right? Beautiful. So this is the new direction. What would be the new position? So my thinking is we're gonna have the position of this face, like we need to somehow get the position of this be I guess yeah, face x, face y. This is relative to the face. Actually, face x and face y, this is probably let me think. This is my position within the face itself, and then have the face of the position in 2D. Sorry, the position. I think I said the face of the position. The position of the face in 2D, and for the back face, that would be y0, 1, 2, 3, and x0. So it's the same as well here. When we are, like, I guess we can do a linear search on this thing for face x and face y. Yeah, right, we have the face. That should also be a constant, but we can, like, it can be pre-computed, but like we can say, okay, B maps to 3, 0, and L maps to 2, 0, and so on. But we have this, and yeah, I think that's a better use for these names, face X and face Y. But how do we find this using this cube map? We're gonna iterate over this. We want to, well, enumerate those. And we want to do what? I guess find the x, y inside of here. This is probably easier to express with a for loop, to be honest. Yeah, but let's try to do it with iterators. This will be a find, but I think we can call it find map because I want to return x, y here. So here we are enumerating. This will be then the y, and this will be the line. And here inside, well, the find map probably returns an option, right? Yeah, sure. Beautiful. So this thing, we are going to expect some of this here. Think of a good message. And then we are going to do something very similar inside of the with a line. So the line, we are going to again iterate and enumerate. We cannot iterate because this is a string. We're gonna have the chars and enumerate them, and we're gonna find. No, still find the map, I think. And in this case, we are going to be taking x and the character, and we are looking for the character that is equal to 2, the face that we are looking for. So yeah, I guess here we can say if this character is this, then return, well, we could be fine using simply find here and discarding the thing that we don't need. So find the character that is equal to the face in this iterator, and this will give me the x coordinate that I want and a character that I won't use. If I expect this, actually all of this goes inside curlies. So then I have the x, and I can just return the x here if I didn't mess this up terribly. Let's reformat. And okay, character here is, yeah, sure, let's dereference. Here you want an expectation message. Oh, actually this should be an optional, because we might not find this thing on the... this should be optional. So we... actually I think we're gonna have something like this. We don't expect this here because sometimes it won't be there. And yeah, I think this is gonna be a find map after all. We can also use filter map or something, or filter first. That, yeah, let's do this. So if this is the case, then some x, right? What? Oh no, some xy basically, because, man, this is confusing. And otherwise, else none. Okay. So this find map should return an option. This find map then should return an option too. What is the... Yeah, no unit, because this should be the case. Okay, and then cannot be... Now it is a character, sure. And this should give me face x and face y, I think. Right, so let's print this thing and see if I actually got the println. And for good measure, let's also panic. I don't want to enter in a infinite loop or something. Face is in face x, comma, face y. Are these the correct types? Yes, they are usices at the very least. So at least typing wise, face u is in 1, 0. That is correct. That is correct. But I didn't actually I don't want to. I already knew that because I could calculate that during this integer division. What I want is like the destination face. So yeah, here we have face x, face y. Actually now we know, okay, we are moving to the right. Let's new face is gonna be the back face, and we're gonna do this mess here, and reformatting changed. Yeah, the formatting changed the formatting considerably. But okay. New face is B. Here we want to find the things that the character that is equal to this new face. Of course, this will need to be extracted, but let's try to solve only this case first. Face new face is in, where are you? Face B is in 0, 3, which is correct. So now that we have face X and face Y, we can do, I think, well, we could do something like, okay, face X is, new X is face X times 50 plus our old X mod 50, and do the same with Y. But since we are also, like, that is not correct, I think, because here we have the transformation of, which is going to be very kind of difficult to express. What am I looking for here? Like now, whatever we have advanced on the X position is going to be transformed into an advance in the Y position. So our new Y is the face Y plus our old X, super confusing. And the new X, we know, is 0, because we are appearing on the left, like this is the thing that is wrapping. So this will be face X times 50, which is like 0 in this case, but like we want to be sort of generic. Like, this is not generic, this depends on like how the face is rotated. What are you complaining about? Yeah, sure, we can convert this now to I32, I guess. What a complicated thing. It's a sign but never used, because we are panicking, of course. Let's print it, this thing. Let's just let's not panic anymore. Let's print ln. Went from face to new face from position X and Y to new X, new Y. And I'm realizing I should get going. So let's try to run this. From face up to back, from position 58, 0 to 0, 158. And then it panicked again. I don't know how to go from face back in direction 0, 1, which is what? It's going down now. Now it's going down from the back face. So we will have to do something similar for the back face. Similar logic to this. Of course, if we are like, this will be many cases. So if we look at our drawing here, from the up face, we can go out of bounds going left or up. We just coded the up case. From the right face, we can go out of bounds going up, right, and down. So we would have to code those 3. So for each face, we have like 2 or 3 cases, like directions that we can go out of bounds. And we need to do the wrapping for each of those, which is beautiful. we can probably express that as, well, what is the new phase that we need to go to, and sort of which rotation do we need to apply to our coordinates. I think so, something like that. Because here, for example, adding the y part here, mod 50, would not make any difference, because we know that, like, we were on y equals 50. Sorry, on y equals 0, because we were in the top row. So this is sort of what is kind of generic. I think this match could return something like let new phase and rotation. Like, it could, return that. Just this would be phase B, and the rotation would be, I don't know exactly, like, how many times you have to rotate your relative coordinates to get the new ones. So yeah, that's, I think, the idea that I can leave for later. Let's add these changes that run like this, and then let's have the dirty phases. The dirty changes that don't compile like this, to remind myself of what I want to do in the future. But gotta get going. This was all for this session. If you have been, thanks for watching, and see you later. Bye bye.